Hello everybody, I'm Soumya, currently working as an assistant professor at Indian Institute of Management, Kozhikode. Today, I am going to talk on statistical analysis of progressive type 1 interval sensor data under competing risk. Now, before I proceed, what I'll do, I'll quickly introduce the sensing schemes, right? And why do we need sensing schemes? So, as we know, in today's world, the industry must maintain the reliability of the products at a very high level. But in order to ensure the high reliability of the products and the systems, right, industries must carry out live test experiments of components and systems at the product development stage. Sometimes it's not possible to continue experimentation until all the items have failed. This is because of the resource constraints. Thus, complete information is available only for a limited number of items. The resulting dataset is actually known in reliability engineering as censored datasets. Now, of all the sensing schemes, type 1 and type 2 sensing schemes are very popular. This is mainly because they're very easy to implement. So what is type 1 sensing scheme? In type 1 sensing scheme, the experiment is continued till a pre-specified time. Whereas in type 2 sensing scheme, the experiment is continued up to a pre-specified number of failures. Now, the limitation of type 1 sensing scheme that since we are limiting the experiment till a pre-specified time, we may not have enough number of failures. Whereas in type 2 sensing scheme, we actually the experiment may go up to a very high amount of time. Another limitation of type 1 and type 2 sensing scheme is that they do not allow the test units to be withdrawn from the live test experiment before the final termination time. However, sometimes intermediate removals of the test units are necessary. Why? The reason behind this is that sometimes it's necessary to free up the testing facilities for the experiments. That's one reason. But a more important reason is that sometimes withdrawals are necessary to gather information on the aging process of the test units. Thus, a more general sensing scheme called progressive sensing scheme is introduced in the literature, where test units are withdrawn at different time points before the termination of the experiment. So what is, let me just quickly introduce one variant of this progressive sensing scheme, that is progressive type 1 sensing scheme. As you can see that here we actually observed the experiment, or we observe the items that's on test at different time points, x1, x2, x3 to xm. Xm is where the experiment ends, and at x1 we actually remove R1 units, at x2 R2 units are withdrawn, and at xm Rm units are withdrawn. Now, the problem with type 1, type 2, and as a matter of fact, the progressive type 1 sensing scheme is that they actually assume that the items on test are continuously observed. But sometimes, because of the resource constraints, it's not possible to observe all the observe the live test experiment continuously. In such situation, what we do is that we observe the number of failures in time intervals instead of observing the exact failure times. This is traditionally known as interval sensing scheme. However, a major problem with this traditional interval sensing scheme is that they do not allow intermediate withdrawals, just like progressive sensing scheme. So what Agarwala proposed, she proposed a more general interval sensing scheme that is known as progressive type 1 interval sensing scheme. So in which we just add the idea of progressive sensing scheme with the interval sensing scheme, and the sensing scheme looks like this. So here we observe the experiment only at x1, x2, and xn, and we look at the number of failures that has happened, let's say within 0 to x1, that is d1, and at x1 we remove from R1 units from the R1 unit 1 units from the experiment. in the similar fashion, we observe D2 failures within the time limit x1 to x2, and at x2, R2 units are withdrawn. Now, how do we decide this R1, R2, and Rn? Typically, they are decided or pre-specified as the proportion of the remaining surviving units at x1, x2, and xm. Of course, uh, we withdraw all survival units, surviving units at xm. Now, coming to the brief literature review, this progressive type 1 interval sensing scheme that has been dealt in the literature in detail, right? For example, as I have already mentioned, Agarwala actually provided classical statistical inference for the exponential model in her 2001 paper. This was further extended to the case of Weibull model, and then for the generalized exponential distribution by Chen and Liu. Bayesian inference for the generalized exponential and Weibull distribution was considered by Lin and Liu, right? And then classical and Bayesian information for the log normal model was considered by one of our papers in 2016. Now, all these papers, the common feature is that they assume that the systems have only one failure mode. In practice, though, the systems may have more than one failure mode, right? And typically, such systems fail as soon as one of these failure modes occurs. So these systems, sometimes in literature, they are also known as the series systems, right? There are a lot of examples of such systems in the reliability literature. For example, Meeker and Escobar, they have provided one battery failure dataset where there are 4 failure modes. Now, as I've told that sometimes these systems I mean, they are actually technically equivalent to a series systems, and the failure modes sometimes are referred to as the components of the series systems. Now, in this paper, what we are going to do, we're going to provide statistical inference, both frequentist as well as the Bayesian inference for the lifetime data under PIC1 schemes, which is the progressive type 1 interval sensing schemes. When assuming that both independent components as well as the dependent components. Now, is there any literature on this? Ahmadi actually considered this classical information based on a class of exponential distribution for such systems, and then they have actually extended the paper for the one parameter proportional hazard family of distribution. Now, in both these papers, actually, it's assumed that the component lifetimes are actually statistically independent. But as Leo has provided us an example where this independence assumption may get violated in various practical applications. Now, in this paper, as I have told that we are actually going to relax this independence assumption, and we're going to work with a gamma fidelity model to incorporate the dependence among the competing failure modes. The independent competing failure risk model can be actually obtained as a special case of the gamma fidelity model, which we are going to present. And of course, we are going to discuss the classical and Bayesian inference for both independent and dependent competing risk model. So coming to the model, we have considered a J component series system, right? So the series system has J components. Let Xj denote the potential lifetime of the Jth component. T denote the system lifetime. Since J component series system stops functioning as soon as one of its constituent J components fails, it is easy to understand the system lifetime is actually minimum of the component lifetimes. Also, let I denote the component that causes the system failure. So it is clearly obvious to understand that for a system that has failed in a live test experiment, we observe the system failure time T and the component which has caused the system failure, which is I. Now, let us assume that Xj follows Weibull distribution, right? So, which is the PDF is given by Fjx, and the survival function of Xj is given by Sjx. Now, it is very easy or standard that we can express this Sj in terms of the cumulative hazard function lambda jx. Now, in this paper, what we have assumed this cumulative hazards, they share a common random probability G, right? And we are going to assume that this random probability follows a gamma distribution with parameters omega and tau, where omega is the shape parameter and tau is the rate parameter. Furthermore, what we have assumed is that conditional on this G, the component lifetimes x1 to xg are statistically independent with the joint survival function given by this Sx. Now, it is very easy to derive that the unconditional joint survival function of x1, x2, xg is going to be given by this x is x. But the problem with this is that we have data here on the pair T and I. So in this case, based on that data set, we cannot actually identify all the parameters of this model, right? So therefore we actually need one more set of restrictions. We further assume here that the random probability, has a gamma distribution with mean 1 and variance nu. So as a result, the unconditional joint survival function of x1, x2, xg will have this form given by Sxx. Now, once we have this, the unconditional joint survival function, we can quickly get the subdensity function, which is given by the little g jt, and we just have to differentiate the joint survival function. Furthermore, we can also derive the expression of the subsurvival function, which is given by this capital G bar jt. Now, it is easy to understand that we cannot express this subsurvival function in closed form. Now, what is interesting here is to note that as this new, the variance actually goes to, or rather, it goes to 0, the joint survival function actually gives us the independent computing risk model, right? So the standard independent computing risk model with variable component actually can be obtained as nu tends to 0, right? In this work, we both consider both independent computing risk model as well as the dependent computing risk model, since the independent computing risk model can be thought of as a special case of the dependent computing risk model. Now, coming to the system survival function, is extremely easy to write the system survival function here. So if we denote the system survival function by ft bar, it can be easily shown that this is nothing but this can be easily written in terms of the joint survival function Sx. So let me just quickly get into the PIC1 data, right? So suppose n items are actually placed on a m point PIC1 scheme at x not equals 0. Furthermore, we let us just assume that the inspection points are x1, x2, xn. Now, here, in case of computing this data, what you observe is the Dij. So what is Dij? Dij is the number of failures that have taken place due to jth component in the ith interval, right? And of course, at each point, each inspection point xi, we have removed Ri systems. So what we have a data set for a m point PIC1 scheme, which I have denoted by eta m. That data set is given by dm. Whereas if you just look at the past set of points in the data set, where it's highlighted in red, D11 actually denotes the number of systems that have failed due to the cause I within the interval 0 to x1. Similarly, D12 and to D1j, and R1 is the number of units which are removed from the experiment at x1. Now, coming to the likelihood function, so given the data set, observed data set dm, we can quickly write the likelihood function of theta, where theta is the complete set of model parameters. Now, what you can observe is that in that likelihood expression, we have these pj's, right? And pj cannot be written in the closed form, as we have already discussed. Now, what is this Pj? Pj is nothing but the likelihood contribution of a system which is failed due to the cause j within the interval xi minus 1 to xi. Now, given the likelihood function L theta given dm, we can quickly write the log likelihood function, which is given by this little l, and in case you want the maximum likelihood estimator of the theta or estimates of the theta, we can quickly maximize this L theta given Dn using standard optimization algorithms. Now coming to the Bayesian analysis, for Bayesian inference, of course, we have to set the priors for the unknown model parameters theta. So let's just assume that pi theta denotes the joint prior distribution of theta. Here, what we have done, we have assumed that all these model parameters are statistically independent, implying that the joint prior is nothing but the product of the marginal priors. Furthermore, what we also observe that each of these model parameters take only positive values. So that's why we have worked with the gamma priors for the subsequent computation. Now, by this theorem, the joint posterior distribution of theta is given by is proportional to the product of the likelihood and the prior. So it's easy to understand that this posterior distribution cannot be handled analytically. So what we have done, we have actually drawn a sample from this joint posterior distribution, and as long as we can draw a sample from the joint posterior distribution, we can compute all the relevant quantities. Now here, what we have used the standard Metropolis-Hastings algorithm to draw the sample from the joint posterior distribution. So coming to the data analysis, Ahmadi actually presented a PIC1 data set on the failure times of radio transmitter receivers. So in that example, there are two types of failures. The first one is the failure due to the failure which is confirmed on arrival at the maintenance system center, which is type 1, and the second type is the unconfirmed failures, right? So there are actually type 1 and type 2 failures. So this is the data set which is given, which is having actually there are 5 inspection points, and what we have done, given this data set, we have quickly checked whether the independent computing risk model is sufficient for the data set, and we have by comparing the models, we have come to the conclusion that the independent computing risk model is sufficient. Furthermore, for Bayesian analysis, we have used Jeffrey's prior as a non-informative prior. Now, if you just look at the posterior densities for the component 1, what is interesting to note, if you look at the posterior density of beta 1 and posterior density of the beta 2, we see that possibly that beta 1 and beta 2 are not significantly different, looking at the support of these two parameters. Now, this is further confirmed by, if we look at the summary table, right, and possibly that these two parameters, beta 1 and beta 2, are not significantly different. Furthermore, what we can comment here is that if you look at even the 95% HPD sets, this is more than 1 in both cases. So both these components have increasing failure rate. Now, in reliability studies, the mean time to failure is extremely important. So we have actually drawn a sample from that mean time to failure for both these components, and this plot shows the posterior density for the mean time to failure for both the components, which is from this plot is clearly visible that possibly the second component has a mean time to failure slightly higher than the first component. This is further confirmed by this table, which clearly shows that the failure time or the average failure time for the second component is higher than the average failure time of the component 1. Now, we have carried out a simulation study for both independent computing risk model as well as for the dependent computing risk model. Let me just quickly go through this independent computing risk model simulation. So we have considered two components, and I have actually worked with 100 systems. For in each case, I have generated 1,000 PIC1 data sets. Now, for the simulation study, we have worked with this eta 1 equals 4, beta 1 equals 2, eta 2 equals 5, beta 2 equals 3, and we have considered 4-point PIC1 schemes with the inspections at 1.53, 4.5, and 6. Furthermore, what we have considered is that 4 different withdrawal schemes Now, what is noticeable here, as we move from scheme 1 to scheme 4, the total time on test is expected to be smaller as we move from scheme 1 to scheme 4. Now, in each case, what we have we have got the average estimates as well as the MACs for both MLE as well as the different Bayesian estimates. What you observe, if we just quickly uh, look at the column highlighted in red, for the MLE, as we move from scheme 1 to scheme 4, the MAC has gone higher. Now, this is expected because the total time on test is going to be smaller for the scheme 4. So as a result, the precision actually goes down as we move from scheme 1 to scheme 4. Interestingly, among this Bayesian estimators, the posterior mode seems to perform well with respect to MAC. However, if you look at the bias, possibly the median is slightly better on most occasions. Now, if you just quickly move to the case of subjective price, so we have considered three different subjective price. So in each case, we have actually fixed the prior variance at the respective true values, and the prior variance are fixed at value 1, 2, and 3. So let me just quickly show you the average estimates for prior one. Here also what we have observed that with respect to MAC, possibly the mode performance slightly better as compared to posterior mean and posterior median, which is very interesting. Now for the dependent competing risk model, I have carried out another simulation study. Just consider the same parameter sets along with nu equals 0.8. Now, we have considered same 4-point scheme, 4-point PIC1 scheme. For nu, I have used a gamma prior with mean 0.8 and variance 0.25. Now, if you just quickly look at the average estimates here, of course, the MLE is not comparable with the Bayesian estimates because we have used a subjective prior here, right? But what you notice here is that, of course, as you move from scheme 1 to scheme 4, the precision goes down. But what is disturbing here that the bias for the new parameter nu is significantly higher. That's one thing. And the other thing, and this is true even if you compare the bias or the MAC with the independent case. So MAC in this case is significantly higher as compared to the independent case. Now, of course, this same observation is true for the Bayesian estimates as well. Furthermore, uh, this what we observed that here also among these Bayesian estimates, possibly the mode performs well with respect to the MAC. Now, this clearly indicates possibly we require a larger sample size in case we want to improve the performance of the estimates. So coming to the conclusion, what we have done, we have considered competing failure modes. We have used a gamma fidelity model to incorporate the dependence among the competing failure modes. And this model is very interesting because we can get the independent competing risk model as a special case. We have provided statistical inference for both independent and dependent competing risk model. We have carried out a simulation study to judge the performance of the point estimators, and what we have observed is that for the dependent competing risk model, the performance actually deteriorates. So a more detailed investigation is required in this context. And of course, we can do further studies on optimal design of the PIC on schemes. So that means how can we actually set up this inspection points and how many units should be removed at each of the inspection point, that also can be looked into. So this can be a potential further research. Thank you. Thank you.